You're right.
Okay, do you want to get started?
Yeah, go ahead.
Okay, I think I was supposed to start. So, well, first of all, good afternoon, everyone, or good evening for our colleagues in Europe. We really appreciate you being online, especially so late this evening. Thanks, Hubertus, for that particularly. Um, so welcome to this discussion on the development of white papers and for the topic of dusty and complex plasmas. My name is Edward Thomas, and I'm co-hosting this session with Truel Hyde, and we have um, four speakers that will be discussing various topics in dusty and complex plasmas: John Goree, Christine Hartzell, Uwe Konopka, and Hubertus Thomas. And I think we'll do a bit more formal introduction in a moment. How we're going to do this is Truel and I are going to do a quick bit of introduction. We'll introduce the speakers and then have them do quick presentations, and then leave hopefully about 15 or 20 minutes at the end for a some question and answer among us in a general discussion. So just in general, I'm going to open up with just a little bit about National Academy's process, how that works, and sort of the critical importance of the decadal process. Both Truel and I had the opportunity in the last year to work with academies during the Plasma 2020, the development of the Plasma 2020 decadal report. Um, Basically, the process is somewhat as Brad described in the previous session. There will be a panel that is formed that will have experts in different topical areas from the rest of the community. What that panel will really do, and their main activity, is going to be reviewing the input from the community itself. And that input is in the form of white papers, as was discussed extensively in the previous session. These papers are anywhere from 4-page to maybe 7-page documents, and they really are a way of expressing the um, the the thoughts of the community to this panel about specific scientific topics, but also representing information about processes, as well as the general direction of the field. And so the community really needs to um, actively participate in this process, both in the context of individual papers as well as group papers. Specifically for the Dusty Plasma panel, and the contributions to be made from the community. Um, there was a, a pretty substantial section in Plasma 2020 about the role and the future of dusty plasmas, which included particularly work in microgravity. Some of the topics that are going to be discussed here also include lunar science, which were not part of the Plasma 2020 discussion. So that is something that should be brought up here. Um, and I think my final comment is just a recognition, I think, that most of the people in this room know, is how interdisciplinary the field of dusty and complex plasmas are. And the fact that it covers a wide span of activities that cover laboratory science, microgravity science, planetary science. And we hope that the decadal process and the input from the community will represent that full breadth. So with that, I'll turn it over to Truel and have him make a few introductory remarks as well.
Thanks, Ed. Well, as you're probably already figuring out, you're hearing some of this more than once. And the reason for that is that we really want you to listen because we really need your help. Obviously, decadal surveys are carried out about every 10 years, thus the name. And the National Academies have been doing this for over 50 years with all the data drawn from volunteers within the broader community that are associated with the discipline and review. So that's an important fact, important statement that I'll come back to in a second. Basically, if you're really a geek and you're interested in the inner workings of this process, there's a really nice document entitled The Space Science Decadal Surveys, Lessons Learned and Best Practices, which was published by the National Academies in 2015. That'll lay a lot of this out in greater detail. And basically, the document shows that the National Academy Decadal Surveys accurately sample, as they're supposed to, the research interest, the aspiration, and the needs of the scientific community under review. And so what's important to us is that this means the decadal surveys report go directly to the federal funding agencies and other government entities, which, as Ed already said, play a critical role in defining what the nation's agenda will be in that science area. So another thing I thought was very interesting was that the report shows that decadal surveys do a good job of achieving community consensus, that there was no evidence of widespread dissatisfaction about the outcome of this process, even though they obviously prioritize science activities. And it's what best we can tell, most of the time, the outcome is not labeled capricious, arbitrary, or tied to the composition of the survey committee, or not representative of a community consensus of the highest profile goals. And that's important because of that, when you listen to the sponsoring agencies, you find a lot of support. It's actually been unwavering. In fact, if you listen carefully to people that are the program leaders at NASA or NSF, you'll hear things like guidebook and blueprint to describe the role these decadal surveys play in the funding, planning, and execution of science programs. Now, that's important for a lot of reasons. As we all know, federal funding is an essential element of the science portfolio, and there's never enough money to go around to support all good ideas. I should know. I have all these good ideas, still don't get support of some of them. The decadal survey acts as a democratic process for deciding how to best direct this resource. And so as such, they help advance the nation's science agenda, providing support for winning approval for important programs, and also acting as sort of a shield against cancellation when difficulties or delays come around, or groups lobby for programs that are not necessarily in the support of the community. Now, having said all that, there are things that every decadal survey has to do well, and each has to draw from the community. And it has to adhere to a process that assures that all ideas are heard. The worst thing that can happen is that a good idea is missed. Additionally, decadal surveys have to demonstrate that the science is the prime motivator and develop a methodology of prioritization that identifies where substantial progress can be made. So this also means that you have to demonstrate to the skeptics or partisans that favored activities or highly lobbied missions are not driving the survey's recommendations. And all surveys have to communicate their conclusions and goals and recommendations to a wide audience of both scientists, stakeholders, politicians, and the public. So because of this, it's really, really important that we have your support and your input. I know that all of us are insanely busy, but let me be clear, the more white papers, the better. White papers do not need to be all that long. As Ed's already said, I'll go him one data and say you could probably do a 2 or 3 page white paper. There's a lot of science out there to explore, but the trick is the committee has to read everything submitted. So if you've got a 2 or 3 page white paper, a lot of times you may get your page read faster than the longer ones. White papers also, remember, white papers can also be directed not just at a specific research or technical topic, but they can also be actually pointed at a policy related to the field itself. So, for example, proposals of new types of research programs, partnerships, international and national, operational mechanisms ensuring support for the science writ large. For example, the NSF-DOE partnership, which is so important to both Ed and me, and a lot of the other people that are invested plasmids, grew out of a decadal survey. On top of that, collaborative papers are strongly encouraged, particularly if you're expressing some sort of consensus within the community. And hint, as Ed already sort of implied, feel free to crib to the most recent plasmid decadal papers. There's a lot of those that are out there. They're all out on the web. So you can at least take a look and see what was submitted to the last decadal survey in a different field, but there's an overlapping field. Now, what's nice about that here is that we've got a really good panel today, as Ed's already talked about. We've got John Goree, Christine Hartzell, and Hubertus Thomas. And they're all going to be giving us 4 representative examples of fundamental physics. So I guess we should introduce them. So I'll do the first 2, and Ed, you can do Hubertus. So John Goree, who will start out today, has degrees from Princeton and Caltech, and is currently on faculty at the University of Iowa. We've been for a while. He's also a guest scientist in Max Planck. And he has research interest, he list research interest in things like plasma physics experiments and modeling, and statistical physics and condensed matter experiments and modeling. But don't let him fool you. He basically likes everything and does it all well. Christine Hartzell is an associate professor in the Department of Aerospace Engineering at the University of Maryland. Her research focuses on the behavior of brains dominated by non-gravitational forces, with an emphasis on the evolution of asteroids and electrostatic forces. She even has an asteroid named after her. You can ask her about that if you're interested. She is currently, she's already said she's currently at the University of Maryland and was a Keck, was a faculty, was a Keck at the Keck Institute for Space Studies, a postdoc at Caltech, and has degrees from in aerospace engineering from the University of Colorado Boulder and from Georgia Tech. So Ed, I'm going to introduce the last.
Actually, Troy, I think you have all the CVs in front of you. So why don't you go ahead? Because I'm trying to pull them up. Yeah.
Where are those CVs? All right. Well, Yui is an associate professor in the physics department of Auburn, and he has been working on space stuff, especially space stuff like the PK4 for a very long time, from his previous connections inside of Germany. His PhD is in physics from the German Aerospace Center in Cologne. I'm reading some of this because I don't have his in front of me as well. And he also worked at MPI, so hopefully I remember this correctly. If I didn't, you correct it later. And worked at the Max Planck Institute at Garching as a research scientist and senior research scientist in the field of complex dusty plasmas. His primary interest in the physics, obviously, of dusty plasmas in general, low temperature plasmas. And he was integral with the PK4 and has been even more integral in the next generation, which is known, well, right now for this week as compact. And then Hubertus Thomas is a group leader at DLR, Institute of Materials Physics. Got his degrees from the University of Cologne and from the University of Munich. He also, again, worked at MPI. And his research interests are low temperature plasmas and complex dusty plasmas, but he also dabbles in atmospheric pressure plasmas, I think particularly in plasma medicine is my guess. And was a responsible scientist for many of the predecessors to the PK4 and has been key PI of the current facility in the PK4 and the Columbus module on the ISS. So, John, if you would you please start this out?
Okay, so I just unmuted my microphone. One thing I don't know how to do is present slides. Can you tell me how to do that?
I think that's happening right now. There you go.
Okay. Okay, so do I just orally say when I want to have a slide advanced? Is that how it works?
I think so.
Yes, please do that, yes.
Okay. Okay, so my name is John Gorey, and I'm just going to give a brief overview about dusty plasmas. The first slide here, there's a little blue star there. It says indicate suggested for a decadal report. Speakers were asked to mark their slides with whatever little bits they were going to suggest might be suitable for a decadal report. And so I'm doing that with a little blue star. Can we go to slide 2, please? In slide 2, I'm introducing the idea of a dusty plasma. What is it? First of all, a lot of people would call it a complex plasma. Instead, in Japan, it would be called a fine particle plasma. I use the term dusty plasma to honor the astrophysicist who originally named it. In astrophysics, small particles of solid matter are called dust, and so that's what I call it. So dusty plasma is a 4-component mixture. There's small micron-sized particles of solid matter, dust, and then 3 other elements common to all kinds of plasmas: electrons, ions, and neutral gas. And these micron-sized particles gain a charge. It can be a very large charge of thousands of elementary charges, which is what makes them do interesting things. Now let's go to slide 3. Why is microgravity the absence of, why is microgravity useful? Microgravity is conditions where you're in free fall so that everything in your experiment's falling together. What's useful about it is you can avoid the situation of sedimentation. Under 1G conditions, when we work in the lab, as in this photograph shown on the left, the solid particles just fall like a rock. They fall like a rock until they get to a place where their large electric field allows them to be levitated. So you can create in this case, a little 2D layer of dust. But if you want to fill a big 3D volume full of dust, it's kind of hard to do under 1G conditions. And so that's why the microgravity is useful to avoid sedimentation. Let's go to slide 4. Okay, I'm now going to highlight the results from one recent experiment that's done on the instrument called PK4, Plasma Crystal 4, which is on board the International Space Station presently. This experiment was done in 2 years ago. The apparatus is shown schematically in the upper left. There's a glass tube under vacuum conditions with the plasma. There's a dust cloud that intersects the plasma, so you get a dusty plasma. There's an ion flow. And so there's something that happens called a dust acoustic wave. This dust acoustic wave is self-excited by ion flow in a plasma, that electric field that is sketched in red in the diagram drives an ion flow. That ion flow makes the particle cloud unstable, and that 3D dust cloud of dust, something that we're not able to easily do under 1G conditions, forms these big waves, and these waves can be seen here. All the little white specks that you see in the video are microparticles that are being imaged by the camera in PK4. Let's go to slide 5. In slide 5, from that very same experiment, I see a still image at the top where you can see that the compressional wavefronts are weakly nonlinear on the left, and on the right, they're strongly nonlinear. Strongly nonlinear, there's immense amounts of compression and rarefaction. And in this particular experiment that was published just this month in Physics of Plasmas, we were able to test some theories for nonlinear wave physics. And the theories are shown there as solid curves, a theory called the conoidal theory. So let's go now to slide 6. In slide 6 is showing now the dispersion relation of those waves. It's a graph of frequency versus wave number. And so that's an observation that we were able to make from that particular experiment. And we were able to compare it to theories for dispersion relation for these kind of waves. Okay, now what I've described so far in these last 3 slides are recent results from an instrument that's now on board the International Space Station, PK4. It's been up there a number of years. In the next slide, what I'm going to do is show somebody else's results, not mine, from a ground-based experiment. Paul Bellin, I think he's probably participating in this in the audience here. One of his graduate students next did this project here where they had in the ground-based conditions, as you can see in the diagram on the left, they had a chamber that has a plasma and a camera with imaging, pretty much like in a lot of these other experiments. And they did something a little bit different. They cooled part of their chamber using liquid nitrogen, and they allowed water vapor in, and they observed particles growing in situ. They didn't use pre-manufactured plastic particles as I did. They were actually growing their particles. And what's interesting is these particles are growing under conditions that are a little bit like those in astrophysics in nebula, where grains of ice might be growing. So in the middle panel, you can see a picture of some of these grains beginning to grow. And in the left, a high magnification image. In the high magnification image, you can see these grains are getting to a substantial size of, many tens or even 100 microns, and they're tending to align with an ion flow. Well, why is that ion flow there? Well, there was an electric field. Well, why was the electric field there? 2 things. It had to be there to sustain the plasma, and secondly, it was helpful in levitating these dust particles so that they didn't just fall like a rock. So all of that's from somebody else's research, Bellin's research, and the bottom panel is my comment. It's not Bellin's comment, but my comment here is that microgravity, what would it be useful for? Well, you might be able to better imitate the protoplanetary conditions by, among other things, possibly by switching the plasma off after the experiment gets started to eliminate the ion flow so that the particles aren't all affected by ion flow in a way that they were not being affected necessarily in the nebula. And under microgravity conditions, turning the electric field off that drove that ion flow won't cause a big problem because the grains won't fall. So that's just a suggestion for a possible future research area that could be done. And that concludes this presentation.
Thanks, John. Christine?
All right. Just waiting for my slides.
There we go.
Okay. All right, so I'm Christine Hartzell from University of Maryland, and the work that I'm going to be presenting today is work from a larger group of folks, many of whom are on this call as well, and who you have heard from already or will hear from shortly after me. But this is the Lunar Dust Remediation Science Definition Team, which has been funded by BPS to look at some payloads that could be placed on the lunar surface to understand dust plasma interactions, as well as test technologies to mitigate the effect of dust on spacecraft or spacesuits in the future. Next slide, please. Okay, so electrostatically motivated dust motion has been hypothesized to occur on the moon and asteroids, and we have some circumstantial evidence that seems to indicate that these sorts of phenomenon could happen. There's been many lab experiments and simulations that have demonstrated the feasibility of electrostatic lofting and levitation, but there's no conclusive observational evidence of these phenomena. Additionally, dust posed a significant nuisance during the Apollo missions and may be hazardous to long-term exploration. So plasma dust interactions may both be hazardous from an exploration perspective, but also could be exploited in order to provide a mechanism to clear surfaces of dust. The prior Decadal survey recognized the significance of electrostatic forces and understanding the behavior of granular materials, and there's still a lot more work to be done in this area. So this topic of understanding dust plasma interactions, especially close to the lunar surface or any surface of a small body, is relevant both from a fundamental science perspective as well as an understanding of the evolution of the surfaces of these airless bodies, and even with implications to technology development and enabling exploration. Next slide. Okay, so as the science definition team, we worked together and sort of identified a series of science objectives that we thought could be accomplished on the lunar surface with varying ranges of technology development that would be needed to achieve these objectives. So some of these objectives can be really classified as measurements or observations of environmental properties, such as understanding the plasma properties near the surface, say as a function of altitude above the surface or time of month. Other science objectives are really exploration motivated. So understanding how dust plasma interactions will influence our exploration operations, as well as how exploration operations, for instance, the impingement of a thruster plume on the surface will change the characteristics of the dust particles or these dust plasma interactions. And then finally, we have higher level goals are just concerning observations of these physical phenomena. So understanding whether or not electrostatic lofting and levitation happen in situ, and making some observations with modern technology to try to constrain these effects. Next slide. So we have 4 suggested decadal contributions. So first, we think it's really fundamental to measure plasma properties near the lunar surface. These plasma properties feed into our understanding of the feasibility of a variety of phenomena, and would be, a great benefit to have these have these nailed down as inputs to simulations or experiments going forward. And the next two science objectives are concerned again with understanding, or at least constraining, whether these phenomena of electrostatic lofting and levitation actually occur in situ naturally or are motivated by the presence of a spacecraft or an astronaut on the lunar surface. And finally, we encourage the continued development of electrostatics-based remediation technologies. So the images on the right side of this slide are some sample data from the electrodynamic dust shields that have been developed by Kennedy Space Center, where basically they have a traveling wave that moves across electrodes and is able to clear dust off of a variety of surfaces. So technologies like this could be, very useful if we have a longer-term sustained presence on the lunar surface. All right. I also wanted to say that the technologies that we've been looking at, they are things that can be accomplished with different instruments that have relatively high TRL. So for instance, if we want to measure plasma properties, Langmuir probes have been flown on a variety of missions. It would just be a matter of customizing this for a payload on the lunar surface. And there's also lots of experiments that can be done in ground-based lab and simulation, as well as ISS or lunar surface platforms. So next slide. All right, so these are just some of the possible instruments. It looks like my Langmuir probe got a little cattywampus there. But these are some of the instruments that we just identified as possible payloads that could be flown to the lunar surface. So in addition to a Langmuir probe, we could also have, a coupon tray where we observe the deposition rate of dust and then test the efficacy of clearing technologies. You could look for horizon glow evidence using modern camera technology. And then a bit more challenging measurement, but one that has been done in other planetary contexts, would be to measure the charge on individual dust grains. And so these were some of our suggestions from this lunar science definition team. That's what I have. Thank you.
Okay, thank you, Christine. Next up will be Hubertus Thomas from the German Aerospace Center to talk a bit about complex and dusty plasma research on the ISS using the PK4 instrument.
Yes, hello. I'm Hubertus Thomas from DLR, and I want to come back from the natural dusty plasmas to complex plasmas. And the reason why we call it complex plasma is to distinguish the natural dusty plasmas from the plasmas with micron particles, which we intendedly put into the plasma in the laboratory. And it's in connection to complex fluids where you have micron particles or solid particles in a fluid. But compared to those which are fully damped, we have the option to go to low damping or even virtual undamped systems, which gives us the possibility to really do dynamics in the system. Next slide, please. As John already mentioned, the gravity is disturbing the complex plasma. And if you really want to investigate the full range of plasma properties, and especially going to large three-dimensional homogeneous complex plasmas, you have to go under microgravity conditions. And we realized that quite early in the research of this field. And we did in the 90s proposals for ESA. John Gurry was one of the co-eyes of this proposal when he was at MPE in Germany. And we did parabolic flights, we did sounding rockets. Finally, we ended up with the German-Russian cooperation on the International Space Station with the first research laboratories, long-term research laboratories, already started in 2001. So next year we will have 20 years of complex plasma crystal research on the International Space Station. So the first two laboratories, PK Nefyodov and PK3+, they were PI-led labs. It was a Russian-German cooperation with very little international participation. Result was about 100 scientific publications, which we gained from these two laboratories. The current lab was different right from the beginning. We were proposing a so-called International Microgravity Plasma Facility in the end of the 90s to an ESA announcement of opportunities with an international team. And this PK4 was one of the outcomes out of this IMF study, which was following the proposal. And beside the European-Russian funding. We opened up this to a larger community. And in the meantime, we have a science team of more than 60 members from all over the world participating in the research. Next slide, please. PK4, as mentioned, is on the ISS since 2014. We had some problems in the first couple of years and until the refurbishment. In 2018, the full objectives of PK4 were not obtained. Now we've started really to go into the details. Now we have about 3 experiment campaigns per year with 4 dedicated experiment runs. Typically, each run has 1 hour, 1.5 hour of pure microgravity time. So if you compare that to a laboratory on the ground, this is really a lot of data which is produced. And up to now, we already published 17 papers from the ISS. Recent examples are so-called electrorheological plasmas. John discussed about recent results from PK4. We were using an AC electric field, which was producing a so-called electric field. Ions were flowing, passing the particles, and in the wakes, they were collected, producing positive ions. And in principle, compared to electrorheological fluids, where dipoles are formed, we can form something similar in complex plasmas. And here's a list of very recent examples, how we investigate these electrorheological plasmas. The first one was looking for the formation of the strings along the electric field direction. And what we saw was a clear crystalline structure along the lines, along the strings. And if you look from one string to the other, the relation was more in the fluid structure. If you look for waves in electrorheological plasma, so in plasmas having these string fluids, then the waves are altered. We see attraction inside the strings. They lead to slower propagation of sound waves compared to what John was showing before. This is a new effect along the electric field lines. And if you use a laser beam to produce shear flow in this system, then you can even measure the shear viscosity of the system. And what we found out is that the shear flow, that the shear viscosity is very, very low compared to ground measurements, which has been done in 2D, but also in 3D systems, in compressed 3D systems. And this is a really interesting result, and we have to carefully look at that in the future. So next slide, please. There are a lot of future topics which will be investigated in the near future. I don't go through the details of objectives. There are also new ideas from proposals from the AO 2016 from NASA NSF. New ideas will always appear while you perform experiments. This is in the lab on the ground, as well as under microgravity, the same. And what should be mentioned here, all can be performed with one setup. So PK4 is a multi-purpose and multi-user facility. And in the moment, we have a guarantee to operate PK4 until the end of 2022. Next slide, please. For the Decadal Survey, I'm now summarizing. Complex dusty plasma research needs microgravity. to fully explore the field. Fundamental phenomena like electrorheology, lane formation, phase separation, and there were a couple of more would not have been discovered on the ground. The ISS is a perfect platform for doing that, and I'm really looking forward what comes post the ISS for research on the microgravity conditions. Complex dusty plasma labs are multi-purpose labs by definition, perfectly suited for large science community. The international complex dusty plasma community is strongly interested in performing experiments, in doing complementary numerical and theoretical models, and also to do data analysis, also applying artificial intelligence methods. So for the future, we should really use the PK4 science team from all over the world to guarantee exciting science. And finally, the ISS is international. Future projects like Compact, which is the next talk, should be international in their realization to really wisely use the available sparse resources on the ISS and to increase the scientific yield. So multilateral cooperation among the ISS partners, among the agencies, and beyond is really requested. And we are really pushing on different knobs. In the moment, you heard already, we were submitting a proposal for the plasma decadal, a white paper for the plasma decadal report. We are intending to write a white paper for this decadal here. And we are also in parallel pushing on the knob on ESA side and writing a roadmap for the future of ISS research. And that's that's the way to get more agencies involved in one research topic. Thank you.
Great, thank you very much, Hubertus. Really greatly appreciated. The final talk in this session is going to be by Uwe Konopka, and he will be talking very naturally about the follow-up experiment to the PK4 experiment, which is called Compact.
Hope I'm unmuted now.
Yes,
hello,
we can
everybody.
hear you.
So I would like to introduce to the most recent development in this space station experiments towards complex plasma. It's called Compact. It was a kind of strange acronym from Complex Plasma Facility, which would be the next generation space experiment to study in general interdisciplinary questions on multi-particle systems down to the atomic, spatial and dynamic levels. And based on our experiment with PK4 in a very wide international and interdisciplinary community. So this is based on a science definition team, which was just recently, a couple of weeks ago, started to actually look again into the science topic, because the pool of potential science topic to deal with is immense, and to make the best selection of the best science, get the best science outcome, and also to actually increase more than it already is the international cooperation and also the expansion towards different research topic out of the complex plasma region, so like planetary science and so on. It's supported by a couple of practically the major space organizations already, and I hope that we get practically everybody involved who is on the ISS involved. And looks like the A from ESA has moved down a little bit. Okay, so next slide. So what do we want to do? So the main point is complex plasma is a unique research tool for multi-particle phenomena, because actually you can go down to the individual particle level and get the full distribution function. And that's for billions of particles practically. To the most extent. So and the pool of potential research is huge. And I just gave a couple of example topics here, which can be studied and which are normally pretty pressing topics. and which are pretty high on our list so far. And that would be, for example, the non-equilibrium thermodynamic issues. So it has to be mentioned that complex plasma is naturally a non-equilibrium system because it consists of electrons, ions, dust, and neutrals, which are simultaneously can be on different temperatures. So usually it's an open system. There's power going in, power going out, and all of these different liquids can be in different temperature, but you still can get a steady state in the system. So if we only look for a single component, like just the dust, you can sometimes treat it as an equilibrium fluid. Sometimes you see features of non-equilibrium systems. Second topic is phase transition. You can study down to the individual particle phase transition of any kind, like the standard one already studied to a good extent is a liquid solid phase transitions, with creating homogeneous or heterogeneous nucleation, and then growing from there the whole system to be crystalline. But you also could potentially study supercooled liquids, or to investigate the glass transition by having a fast cooling method, or which compact would be predestinate to compress the system rapidly and therefore increase the coupling and therefore get a transition in this way triggered. You could look at the hydrodynamic and especially turbulence. How is the turbulence actually starting on the atomic scale, and how does the energy input, or the energy distribution on the atomic scale actually influence how the instability evolves? And there are other topics like active matter, how particles where you induce energy, like two-phased particles with different surface, and you induced energy by those particles in the system, and if they practically lead collective behavior in the system, and with the analogy to other active matter systems. And the main thing is also now different than the first four topics. We really would like to expand to different research fields, like planetary dusty plasmas, or soft matter, granular matter, colloidal science, or geophysical science. And we really need to have the input from those communities about what this complex plasma experiment could do for them, because it's a big investment, and as large as the community, as more scientific outcome we will get. And as an example for planetary dusty plasma, I mention here the charging of lunar regolith, and developing potential possibilities for control, transport, or mitigate dust. And you see this in the SDT talk for the lunar dust. Just here on the left, on the right, you see two examples actually where a complex plasma is used for crystallization. You see crystallization fronts on the atomic level. On the right side, you see actually a turbulence in a curved flow. Okay, next slide, please. Ed, next slide. Oh, thank you. Yeah, so how do we do that? So where is compact compared to the other space experiments? So here you see the timeline on top. There are all the experiments since 2001, Pika and Nefedov to Pika 4. Pika 4 was a slightly different because it addresses more systems with anisotropic potentials and more liquid systems. And so compact is more in the history of Pika 3 Plus, which was a smaller parallel plate discharge chamber, and where you can get maybe, let's roughly estimate, like 10 million particles or 100 million particles in the system totally. And on the bottom, you see a picture where it's written microgravity on top of this. That's actually from Pika 3 Plus, where you see a cross section of such a dust cloud, and you can resolve it to the individual particle. And here you see clearly on the left the picture from them, that under gravity condition, the similar setup. You practically compress the dust cloud, and it's because of sedimentation, you can barely study 2.5D systems. The compact system is now first 12 years ahead in technology, roughly, compared to the Pika 3 Plus, and therefore the tremendous impact on what can be done with the system, what data rate you get, and all the technology we put in the original design. And on the bottom right, you see actually how it's used under gravity condition, and this cloud is already kind of bigger than the microgravity one on Pika 3 Plus, and you can imagine how it would be under microgravity. So there you have the transition, practically the continuous media. You can get maybe 100 billions of particles potentially in the system and then study the behavior there in cross-sectional or even with 3D optics. Major features of this new device is, okay, it's a vacuum chamber, so any experience you think of it can be performed in a vacuum chamber like that, like a liter vacuum volume, which is not complex plasma, might be doable there too. There are dust dispensers from the outside shaking dust in. There's gas support system. There's a complex radio frequency system as well as a electric field system. You can maybe design some forms of traps, and you can actively manipulate the internal geometry, like you can move the electrodes and compress the system while the system is, for example, crystallizing. Can we see the last one? The next slide, not the last one. So how far is this development of this experiment? So they started maybe about 2007 with pre-development, and there were a couple of different changes in name and development phases. So now in 2020, since it was planned as a huge facility, now we reconsider to actually, for the best science selection, shrink it down, collect all the science also from different fields, and therefore we in January will have a compact science definition workshop. Unfortunately, the symbols went across all this thing. So if you have ideas and want to join, I will soon send out some flyers so that you can join this workshop and bring in your perspective from there. And so hopefully within 2 years we will have defined the science and then go to a transitional part to actually build the experiment and maybe launch 2027. It would go up to the end of the decal part. And to mention here, it wouldn't be just using the ISS. It's usually also using other carriers for microgravity, like parabolic flights are usually used a lot to make experiment preparation, checking that all the technology works, and then actually preparing experiment, which will be finally done on the ISS. Okay, the last one. So I put in 4 bullet points mainly to summarize what's the major important thing here, that complex plasma are really unique for studying multi-particle systems down to the atomic scale, and they are up to undamped systems, so they're unique. And I don't know any other system like this, which you can use in this way. And it definitely needs microgravity. So this is mandatory to get homogeneous and large systems, so to reach a continuous media. Using the state-of-the-art technology and the hand manipulation techniques we already developed, of which you can adapt a couple of things, maybe to add more experiment topics, we probably can go into the limit of continuous media and explore things even outside of complex plasma research. Yeah, the research question should be broad, the community should grow, and therefore we have a science definition workshop, and the science definition team will in the next month actually collect all this information and sort it. It should be finally a multinational, multi-agency, interdisciplinary, campaign-based facility. And I hope that all agencies who are participating in the ISS will be on board at that. So that's my vision here, presented for the SDG.
Great, thank you, Uwe. And I also want to thank John, Christine, and Hubertus for really great presentations on the status of dusty plasma research and outlooks for interesting projects going into the next decade. We had a couple of questions that had come in before the session started. I'll turn it over to Uwe, to Truel, sorry, to just quickly discuss those questions. And I would certainly encourage, if anyone has additional questions or comments while we're doing this, to also put them into the chat. We have officially about 10-ish minutes left in the session, so we want to also be respectful for all the time, especially for our colleagues in Europe, because it's quite late there. So anyway, so Truel, do you want to take over?
Sure, I'd like to thank the panelists as well. You did a great job, as we knew you would. And we've got a couple of questions, as Ed already said. We've only got, as he said, 10 minutes. So I'll just start with the easy one. Is there some way that you can obtain simulant without having to have a full award for, say, dusty plasma experiments that may be funded on other grants? And I can answer that one, and anybody else in the committee can add to it if they wish. But yes, there's certainly a way of doing that. There are several different types of places in which you can get simulants of all sorts, Mars or lunar or whatever, either from NASA, very expensive, or Exolith, not nearly so expensive. So anybody else got anything they want to throw in on that one?
Yeah, we got lunar simulants just recently, I think from a Florida company, and it's
Yeah.
like $30 a kilogram or so like that.
Right.
Yeah,
So if you
and I'll
wanna
point out
just- But
that Addie Dove also put a link to that in the chat as well.
oh, excellent. Okay. So yeah, there's that's exactly one of the places we've gotten simulant. So there are many places that you can pick up some simulant and do some work of this sort, and it won't necessarily break the bank. So that's good. Here's one that well, there's two that are a little bit interesting. So I'll hand these off to Christine, or at least one. She'll love me for it. So it may be useful to consider developing a synergistic roadmap regarding the study of dusty plasma interactions on the moon and on other airless bodies, asteroids, comets. So I know we've actually been talking about that. So Christine, you want to say a little bit about where you think this might go?
I mean, there definitely is a synergy there. Since the moon is such a big push right now, and we're looking for payloads to be on the moon, to be, serviced by astronauts potentially on the moon, I think that that's kind of where the emphasis for the moon came from BPS's perspective, since they're transitioning from an ISS set of experiments. The next sort of lab would be a lunar-based lab, but there's definitely similarities in the science questions there. And any sorts of measurements that we make on or near the lunar surface are going to inform those models that we use to apply to other planetary bodies. So I don't know if anyone else has any comments on that, but those would be my thoughts.
No, I think that's exactly right. I mean, we have very little data on airless bodies of any sort. So obviously the moon is the easiest place to get the first round of that data. So I think that's good. So here's another one, again, sort of geared towards the moon. So either Christine or John or Hubertus or Yui or whoever wants to, this is pretty much open to all of us. This person has an interest in low TRL plasma physics concepts that might end up as near-term enabling technologies in support of NASA ionospheric or magnetospheric or lunar surface, subsurface missions. So that's pretty much an open question that leaves us, gives us the ability to burn the next 7 minutes pretty quickly. But does anybody want to jump in on that one?
Can you repeat the question?
Sure. It's pretty open-ended. This person has an interest in low TRL plasma physics concepts that might end up as near-term enabling technologies in support of NASA ionospheric, magnetospheric, or lunar surface subsurface missions. So it's pretty much open to the world. So do we have anything right now that already has, I guess I would rephrase the question slightly and say, is there anything out there right now that we're aware of that's already at some TRL level, even a low TRL level, that might be easily extended for use in other places, not only on the moon, but elsewhere?
I mean, I guess I would say that it's not directly a plasma topic, but it is related to this electrostatic dust lofting, would be the, Kennedy electrodynamic dust shields, which is basically, this electrostatic lofting concept without a plasma. As far as funding for those types of topics, I think that STMD is the place to go. So, they have the NIAC solicitation, which would be a great place to propose a low TRL technology that could in the future enable a mission, because they're really particular about, developing a technology in a mission concept. So that would be where I would look for a topic like that.
Mm-hmm. I think that's a good answer, actually. And I do think there are, well, I mean, one of the first things you should do is probably take a look at what's already been used in the environment, because as you know, the dust lofting, we started out by looking at, cameras that have been used on the moon that have seen something of that sort. So there are some technologies out there that are easily upgraded to a fairly decent TRL that could be used in several different types of avenues. And since I guess we've only got 3 or 4 minutes left, I'll end with, seemed like there's one other one. Oh yes, Addie just added to the chat list, in addition to the link, the statement that the ISS microgravity environment is also very applicable to asteroids and other small bodies, which is exactly right. So that's, it would be nice to be able to, that's another one to add to the list for Hubertus in terms of things that we can do on the space station that would be applicable to a lot of different places.
So Troll, if I could throw in just 2 quick points as we're getting ready to close. One, just in general about as this community is thinking about the types of comments and the kinds of projects that can go forward. There was a question in the main session about connecting to other agencies, and I would point out that that in the plasma decadal, one of the big points that was made there was not only is the field of plasma physics as a whole interdisciplinary, but it actually covers topics that are of relevance to multiple agencies. And the kinds of scientific questions that our panelists have discussed are more than just things that can sit in NASA. They can actually sit possibly in NSF, possibly in DOE, and so as we are thinking about how to respond to this call for white papers, I would encourage people to look at Plasma 2020. There was a very large table in there that discussed overlaps between agencies. And I think if this community can reinforce that in this survey, that there are opportunities to look at cross-agency collaborations, I think that would be that would be really powerful. And my final comment is the fact that this is the fundamental physics program, but we can't do fundamental physics without some of the technology to enable us to be able to do that. And so I really like the point that Christine made a few moments ago about doing technological developments. It's also about laboratory work. It's also about low TRL technology, and all of that sort of together creating a path forward. And so I'd invite any of the other panelists to comment on that as well.
I think they all went home or went to bed.
Yeah, fair enough. It's also really been a really long day for everybody.
It's been a long day. Well,
So
I guess we can start by thanking our panelists one more time, and also everyone that came to listen. And please contact any of us if you have additional questions. Ed and I are always glad to talk to people about dusty plasmas.
and this session is being recorded, so I'm hoping that once the links go live, you'll be able to distribute it beyond the group that was here as well.
Yeah.
So and I extend my thanks to everybody as well. This is really great.
Yeah, and if you have any ideas of your own for utilization of compact or so, feel free to contact me, and we will put it in the list for the science definition team.
Great. That's the best deal I've heard in a long time. Sounds good. All right. Well, thanks, everybody. Have a good night.
All right. Thank you all very much. Bye.
Bye.